Buon pomeriggio a tutti, grazie per essere venuti qui all'ultimo seminario del Dipartimento per questo semestre, poi cominceremo il prossimo semestre. Oggi abbiamo il piacere di avere Carlo Arosio, che sta all'Institute of Environmental Physics di Bremen. Si è laureato all'Università di Bologna, poi ha preso il PhD proprio a Bremen e adesso sta proprio facendo un postdoc presso lo stesso istituto e ci parlerà del ozone related activities in Bremen from the stratosphere to the troposphere. Allora abbiamo come tempistiche fino alle 3:30 massimo.
Direi che ce la faccio.
Ok, vi ringrazio.
And I speak in English, right? Okay. Should be fine for everyone. Yeah, thanks for the invitation, for the introduction as well. Yes, so I'm working in Bremen, but I'm spending 6 months in Rome, close to Rome, in Frascati, in ESA, Esrin, so that's why it was easy to arrange today and to come here. So I will talk about indeed ozone activities. Do you hear me? Is it fine? A bit, but okay. I try to speak better. So I go from stratosphere, what I was doing mostly in the PhD, to touching a bit the tropospheric ozone at the end of the presentation. So it will be divided in 3 parts. First, the stratospheric ozone retrieval in Bremen and the usage of limb observations. I also don't know how familiar you are with limb observation, stratospheric, so I will just give a short introduction at the beginning. I don't know. Then I will talk about the merging of Schiamaki and OMPS datasets to study long-term trends in the stratosphere, and then go into the tropospheric ozone using this limb-nadir matching technique to derive indeed tropospheric ozone columns. Okay, Bremen, we were talking before, is mostly famous for the 4 town musicians with the statue in the town, and yeah, it's an Hanseatic city in north of Germany. So a short introduction about ozone. Maybe you already know about everything, but just to give a short introduction, we are interested mostly in the ozone recoveries nowadays. The stratospheric ozone underwent a strong depletion at the end of the last century, and then with the Montreal Protocol, I mean, the ozone depleting substances were banned, although some illegal emission of CFC-11 were detected in recent years. But overall, due to the ban of ODS, due to the increasing of greenhouse gases and the cooling of the stratosphere, these 2 main reasons, we expect an ozone recovery or super recovery, depending indeed on the amount of also increase of greenhouse gases, and also depending on the emission of N2O during the 21st century. Several studies addressed already the discovery of the recovery and the trends using several data sets. These are all satellite data sets and some model simulations. The main problem is related to the fact that the trends that we have observed are relatively small, so of 2-3% per decade in the upper stratosphere, and the uncertainties related to the trends are generally large. Okay, just slept? No, it's fine. They are generally large, so we need long-term satellite measurements and also a very good stability in order to detect small trends over relatively short time, because we have like 20 years of recovery, and still it's kind of short to clearly see it. The tropospheric ozone that I will talk about at the end of the talk, it's related to tropospheric smog, to summer pollution. So it's formed in the presence of NOx, of volatile organic compounds and sunlight, and yeah, it's a problem especially during summertime in cities, and there's a negative effect on human health and plants. And so the questions related are questions related to tropospheric ozone are in connection to the policies that have been introduced by government to reduce ozone concentration and regulation of pollution in general. So, going to limb observation in Bremen, the remote sensing group was developed or was born in connection to the Schiamacchi mission at the beginning of the century. Schiamacchi was a limb and nadir sounder on board of Envisat, was launched in 2002 and operated until 2012. Here you see on top the schematic diagram of the limb observation, and limb, you kind of, the line of sight of the satellite goes through the atmosphere, and these are shortwave observations, so the solar radiation is absorbed and scattered in the atmosphere and then goes into the line of sight of the satellite, which is a passive sensor and receives the scattered solar radiation. Schiamacchi, and then told about Schiamacchi. OMS is another instrument, also a limb sounder by NASA, launched in 2012, and they both share a common observation technique, common geometry, although a different spectral resolution, and we applied a similar retrieval algorithm to retrieve the ozone profiles from both of them, and now I will shortly introduce it. I will focus on OMPS because it was the work that I mostly done. So we use sun normalized radiance, and we select 4 spectral ranges, 2 in the UV and the Chapuis band in the visible. And these different spectral ranges are used to retrieve ozone at different altitude ranges. So here on the left. And so we get a profile generally from 10 or cloud top height to 60 kilometers generally. And the voltage transfer model is Schiatron, which has a name related to Schiamacchi indeed. Yeah, the retrieval algorithm is based on spectral fitting. So this is schematic diagram that, so the Schiatron model simulates radiances, it compares with the observation, and depending on the agreement, the ozone profile is modified until convergence, until the differences is below a certain threshold. We need for this information about clouds, which need to be filtered out, and also the aerosol extinction is relevant because it has a large impact due to the very long line of sight of the satellite. We also need a accurate aerosol extinction profile information, which is retrieved also from OMS observation in this case. Yeah, the validation of the data set is performed either with independent data sets, for example, MLS, this microwave limb sound, which is kind of standard reference measurements, satellite measurements, or with ozone zones in the lower part of the stratosphere. Here I'm showing observation from l'Aquila. This on the left, the comparison mean profiles, ozone zones, and the IUP OMS in red, averaged over 13-14 years. And so these are collocated measurements. We select, so it's within a day, 12 hours, 5 degrees latitude and 10 degrees longitude. So we have collocated observation profiles. And here on the right, these are monthly averaged collocated measurements. And so we can also check the stability of the OMS dataset in general at different altitudes. As you can see, in the bottom, so in blue, it's 14.5 kilometers, so lower stratosphere. We have a large scatter, and also the stability is not so great. I computed so these are relative difference between OMS and zones, and you can see, and I computed the trends until 2020 because in the last few years there are some gaps. But in general, so here is the trend of the differences, linear trend of the difference with the uncertainty, and in general from 20 kilometers, there is a drifted small or generally non-significant, so it's pretty stable. Okay, so I would skip this one because it's not so important. Let's go to the merging then. So we have we retrieved the ozone profiles from OMPS. We have at IUP in Bremen an existing data set of Schiamacchi measurements. As I said, these two data sets barely overlap. Just at the beginning of 2012, there are 2 months of overlap, and MBSAT failed, and OMS started the measurements. And the plan is also to use a new instrument that NASA launched last year. It's again called OMS on board the NOAA 21 satellite. So we have measurements from the beginning of last year. The retrieval is also in test phase, but I will focus here just on the two data sets. And since they have a very short overlap, we need a transfer function to merge them, to debias them. So we use this Aura MLS, which indeed standard and it has a very long observation time series. It's still measuring, although it's planned to be switched off or terminated in 2025. So it's just 1 year left, unfortunately. So we use anyway this data set to debias the two. Since they share a very similar geometry, they have a very similar seasonal cycle, the two Schiamacchi and OMS time series, and also very similar, let's say, spatial coverage. This merging has been done simply by debiasing the two. So we use monthly averaged ozone profiles. They gridded in a regular 5 degrees latitude and 20 degrees longitude grid. And vertically, we kept the Schiamacchi 3.3 kilometer steps from 10 to 60 kilometers. In yellow, you see the very short overlap of the two, and in green, the MLS time series. So we compute the bias between MLS and Schiamacchi and MLS and OMS, and we subtract the two to then bring them at the same mean level, so to say, and merge them. MLS is not part of the merged data set that you see here. Here's just an example of the merged data series on top, and on the bottom the standard deviation of the time series, and on the most important, I would say, on the bottom right, you see the drift per decade with respect to MLS, because we want to be sure that the merged dataset does not have a significant drift, because we want to use it to compute trends. And you see that in general, so the dashed lines are where the drift is not significant. So the drift is just the linear trend of the differences, and just in the lowermost stratosphere on 20 kilometers, we see a positive drift. This is probably due to the interference of the Hunga-Tonga eruption last year, 2 years ago now, in 2022. There was this strong volcanic eruption that perturbed, especially in the tropics, the retrieval. So we need to mask out some months of the measurements here. But still, there is some residual impact that probably has to be screened out as well. Anyway, we used the merged dataset to compute trends. Here I just put the multilinear regression model that we used. Essentially, it's a classic multilinear regression model in which we have a linear trend, and then we take into account several proxies other than seasonal terms, of course. Also, indeed, variables or phenomena that impact the ozone time series, like the QBO, the solar activity. AOD is the aerosol optical depth, which should take into account, for example, high aerosol loads in the lower stratosphere, the ENSO. And we also include some dynamical proxies, like the AO index and the heat fluxes, to be taken into account the atmospheric dynamics in the especially in the polar regions. And with this model, we applied to our Skia plus OMS merged datasets. And this work was a bit done also in collaboration with the University of Leeds. They have this Tomcat chemistry transport model, which is forced with era 5 meteorology, and we were interested in comparing the two time series. This model also covers the same time period, and so yeah, we kind of ran this comparison study. You can see zonal trends. These are latitude versus altitude trends, period 2004 to 2021, so without Tonga Tonga. We see the expected ozone recovery in the last 20 years, so with positive trends in mid-upper stratosphere, especially at mid-latitudes. In the lowermost stratosphere, we see negative trends, which are also reported, although non-significant. Again, dashed lines are non-significant trends at 2 sigma. Also, other data sets have shown a negative trend in the lower tropical stratosphere, which the model do not reproduce. And I would say that in the tropic, we see the largest discrepancy between the merged data set and the model, especially indeed in the bottom part, but it's a known issue. What was most interested actually to do with this dataset, since it's longitudinally resolved, most of the datasets are zonally averaged, but since Schiamaki and OBS have a larger spatial resolution, we could also have the longitudinally resolved trends. And we compared those with Tomcat. We noticed this zonal asymmetry, longitudinal asymmetries in trends in polar regions, where we have positive trends over the Atlantic and negative at other longitudes. And it's this is on the left and the right. It's like a slice of the stratosphere at 65 north, and we see that this asymmetry is vertically consistent. We have positive indeed over the Atlantic longitude, and negative is also in the lower stratosphere. And Tomcat can reproduce it, this feature, this pattern pretty well. And looking at the seasonal resolved trends, we notice that this asymmetry is largest during late winter and early spring. So these are trends in March, April, and we see indeed this bipolar structure, so to say, which is not reproduced by temperature, because we are in the middle stratosphere. We thought that maybe temperature could have a impact on this, but it doesn't seem so. And we kind of find out also with the usage of Tomcat that the atmospheric dynamics changing in stratospheric dynamics changing in the position of the polar vortex have been affecting the ozone distribution, of course, but also trends being also having also the position of the polar vortex and the potential vorticity here on top, some trends or some, would say, decadal oscillations that indeed kind of have an impact on the ozone trends, and they are the responsible for this asymmetry. But okay, going down to the troposphere finally. So before we use the merged dataset or the stratospheric part to compute trends, now we can actually combine stratospheric measurement with total column measurements to derive tropospheric ozone. This is indeed this Lim-Nadir matching technique. We can do this because both Schiamaki and OMS perform measurements, as I said at the beginning, in limb view, but also in Nadir view. So from the limb we get indeed information about the stratosphere. From Nadir we get information about the total column. And so an IUP and a colleague of mine developed this retrieval of the total column from the Nadir mapper. And we use indeed this IUP OMS stratospheric product that I presented to get information about the stratosphere. But the problem is that due to clouds or large aerosol load, sometimes we cannot reach the tropopause height. We derive the tropopause height from ERA 5, but sometimes the stratospheric profile do not reach down the tropopause height. So we need some climatology to complete the profile and then subtract the total column, subtract the stratospheric column from the total column to get the tropospheric ozone column. So this is the method indeed applied to OMS, and the same was done by Schiamacchi. Actually, Schiamacchi performed like even the same sensor performed the just with a switch, the limb and the nadir scans, but in principle it's the same approach. So this is just an example, a map of the tropospheric ozone column, average over for OMS, average over 6 years of data. We see several structures. I would say, of course, we expect low ozone over high topography terrain areas. And we have a typical, it's called wave 1 structure with higher concentration of ozone over the Atlantic and lower concentration over the Pacific. This is related to the emission of ozone precursors, especially in the African sector and over the Atlantic, which is affected over the Atlantic sector, and which gives leads to this distribution, typical distribution in tropospheric ozone in the tropics. And we also see a kind of artifact with a positive band of tropospheric ozone in the Pacific, right at the equator, which is an artifact coming from the limb profiles. Anyway, we got these two data sets indeed, Schiamacchi and OMS here, just to show the overall comparison. This is an average over the two. You can already see that there is some overall bias between the two. Schiamacchi generally gives a larger ozone loads also here reported than on PS, but generally the structure of the distribution of the pattern is similar. And again, my colleague was comparing again the tropospheric part again with ozone zones. Now we can integrate the ozone zone to get the tropospheric ozone column and compare then. These are just, sorry, I didn't have l'Aquila data, but I put like Hilo for the tropic and Madrid for mid-latitudes. So in red it's zones observation, and then we have in black, blue, Schiamacchi and OMS time series. And we see indeed here that there is kind of not only a bias between the two, but also they have a different seasonal cycle, especially at mid-latitudes, with Schiamacchi having a larger seasonal cycle than OMS. And the plan is again here, the merging of the two data sets. I said that I'm visiting now Esrin in Frascati. That was a bit the work that I've been doing there. Due to the fact that indeed there is a larger bias between the two and a different seasonal cycle between OMS and Schiamacchi, we need again a transfer function, which now in this case we selected OMI MLS, which is another NASA-based tropospheric ozone dataset. But we need first to compute the seasonalized anomalies, so we remove the seasonal cycle as reported here on the bottom, and we compute we debias the two with respect to again OMI MLS, and then we have to add back an average seasonal cycle between Schiamacchi and OMS to have a reconstructed time series, which is here compared with the OMI MLS. This is a bit again work in progress, and indeed this is the last slide. What I'm doing now about the tropospheric ozone data is indeed to use to finalize and use the Schiamacchi OMS tropospheric ozone dataset and to compare intercompare it with other available limb-nadir matched datasets. These are from different groups from NASA, from the Finnish Meteorological Institute and DLR, to understand. These are in theory very similar datasets, but in practice they can be pretty different because they use also a different definition of the tropopause height or different merging techniques. So it's in the end they are not so well comparable, unfortunately. But it's good to also, I mean, the final goal is to have a look at the trends in also in tropospheric ozone, and also to understand better which proxies are useful and needed to compute the trends. Here on bottom you see the influence of ENSO and QBO also on tropospheric ozone, and so this we also need either a multilinear regression model again, or there are also other techniques that take into account outliers in the time series that maybe are more suitable for the trend studies in tropospheric ozone. Yeah, so I am done with this. Thank you for organizing the meeting. I can actually invite you on our Bremen seminars. We do every Friday afternoon during the semester. We have Friday seminars, and we also used to invite external people, so we can actually interact if you are interested in presenting something. It's generally more about what also satellite observation generally, or ice and ocean topics on Tuesday, but indeed maybe we can find some topic in common as well. Thank you so much. I was shorter than expected, so that's good. If you have any question. Wait a minute. Yes, yes. They met this tropospheric. That's true. You need to collocate. You need to collocate them, because indeed Skiamaki, I just mentioned, Skiamaki was indeed was designed to do this limb-nadir matching with exactly, so to say, so that first it was, I don't remember first or later, first like observing in limb, I would say, and then I don't know, with a few minutes delay observing the same scene in nadir. So the matching it's already done, so to say. For OMPS, we have different sensor. One sensor is dedicated to the limb observation, one sensor dedicated to the nadir observation, so that we actually need to, and they also have different footprints. So my colleague indeed was doing the merging, and so you have to kind of indeed find the collocation, and then I guess she was averaging like 3 nadir pixel to get and collocate to the limb profiles. But this is the same orbit measurement, so they have just like probably 7 minutes difference between the two, so they are kind of compatible. Okay, so different data sets. This one. So these are mostly based on observations. Yeah, the name of what you see, the name of the data sets already speak about the observation that are used. For example, OMI-MLS is a combination of OMI for the nadir, so total column, and MLS for the stratospheric part, or OMPS MERA. This is OMPS for the stratosphere, and MERA, it's a chemistry transport model for the total column. So some of them actually use model or kind of a simulated observation, like here it's Basco, it's another model, or okay, OMI limb, it's again OMI and limb. They are taking into account several ESA-based stratospheric observation from Skiamaki, MIPAS, from beginning of 2000 until now, and OMPS as well. Yeah, so we are the only one which are doing the merging of two different data sets, but yeah, I mean, overall you see that they all reproduce more or less the same pattern, I would say. The details are different, and also the average values in general that they provide, due to also the different tropopause definition, they can be different, they can be offset. Yeah. Yes. Ozone zones. Yeah, it would be good to have to have a bit more often. Yeah, because I mean, especially when you compare the monthly time series, then it's, if you have like, 2 ozone zones per month, and then you compare the satellite data, it's hard to actually find a good correlation. So that's why we need collocated measurements, but then you reduce a lot the number of free collocation. If you remember, I am using pretty large collocation, or how do you say, collocation criteria are not tight, because indeed you need to find a large enough sample to do this. And so yeah, would be nice to have a bit more often. Would be indeed, yeah, yeah. And also continue the time series as much as possible, as far as possible, because indeed, okay, l'Aquila, it's already good that it's pretty stable. Okay, the last few years not so much, but then we have, I don't know, some station that stopped some years ago, some just started. So it's nice to have a long and homogeneous, more money, and also like homogeneous data sets, because good. Thanks to you for the invitation.